Okay, now for the football example. This is a little bit different. It's an angled projectile. So we're starting off with our initial velocity up at an angle, 60 degrees in this case. We're told the ball is kicked at 18 meters per second at that 60-degree angle, and then we're asked to find a few things here. The first thing we need to do is to break our velocity into x and y components. We need to componentize this. Because we can't deal with it at an angle, we need to treat the x and y components independently. So using SOHCAHTOA trig here, we'll end up with the x component of 9 meters per second and the initial velocity in the y direction 15.6 meters per second. Now, like we talked about in class, I drew this very large relative to the trajectory of the football, just so we can see it better. But in reality, all these two components, the total 18 meters per second, they're occurring only at the instant the ball leaves the kicker's foot. Once it leaves the kicker's foot, gravity is taking over on the football. We know this 15.6 meters per second is going to start decreasing as the ball goes up. The 9, though, does remain constant because there's no acceleration in the x direction. There's no net force, nothing to push it or to hold it back in the x direction. Okay, so for part A, we're asked to find the height of the ball at its peak. So that is right here. We're looking for that. Okay, so part A, in the y direction, we're looking for that maximum height. All right, now the maximum height occurs obviously halfway through the flight. So we're only going to look at half the flight in this case. So we're looking for that displacement. We know the initial velocity is 15.6. We know our acceleration, gravity. All right, and then we need to know one other thing, and that thing is going to be the final velocity. So right up here, the velocity in the y direction is going to be 0. We're going from going up to going down. So at that instant, it's changing directions. So we can say the final velocity is 0 at that point. Then we can use v squared equals v naught squared plus 2a delta x. Plug in our values. So we've got 0 equals 15.6 squared plus 2, negative 10. And then we're looking for that height. So when we solve that equation, we should get 12.15 meters. Whoops. Okay, so there's our maximum height. That's part A. Part B, the speed of the ball at the peak. All right, well, it's not asking for horizontal, it's not asking for vertical, so we have to consider the total speed at the peak. It is still moving in the x direction at 9 meters per second. The velocity in the y direction is 0, so that total speed at the peak then is just 9 meters per second. Part C, the horizontal range of the ball. So here we're looking for that total horizontal range. All right, so I'm going to try to squeeze all this in right here. Okay, for that, that's in the x direction. So we're looking for that delta x. Okay, we know the velocity in the x direction is 9 meters per second. We need to know something else, and that's going to be time. In the x direction, we only have 3 things: displacement, velocity, and time. So we can get that time from the y direction. All right. So we have a few options in this case, like we talked about in class. All right. So in class, we talked about the time it takes to go up to the maximum height should equal the time it takes to come back down. That's only under one specific condition, and that is if it lands at the same level it's launched from. That is the case in this problem. We do have a football leaving the ground, it lands on the ground. So that would be true. Our initial velocity is 15.6. Okay, we could look at the final velocity here is 0. We could get the time to take sakes go up. We have to remember to double that to get our total time. Okay, like I mentioned in class, a lot of times I forget to double that time and then I get the wrong answer in the end. So I don't really like to use that one. I like to look at just get the time for the whole thing at once. Okay, so we're going to look at the whole flight for this one. Okay, like I said, you can always get that time for halfway and remember to double it. All right, so we know acceleration, -10 meters per second squared. We can say the displacement in the y direction is 0. It starts on the ground, it lands on the ground. We don't care how far it went in the x direction, we're only looking in the y direction here. So as far as the y direction is concerned, displacement is 0. One other thing we can say is because it leaves the ground and it lands on the ground, we can say the final velocity is -15.6 meters per second. We talked about that in class 2. The speed up equals speed down as long as you're landing at the same level you left the ground from. All right, so we've got a few options here, but we are looking for time. Okay, so I'm going to use these first three with time. So the equation I'm going to pick, delta x equals v naught t plus 1/2 at squared. So I've got 0 equals our initial velocity, 15.6 times time plus 1/2 -10 times squared. Okay, I can move this -5t squared over the other side, divide everything by time, so we end up with a pretty simple equation, just 5t equals 15.6. Alright, it's not a quadratic, it kind of looks like a quadratic, but here solve for time and we get 3.12 seconds. So we can use that up in our x direction. Time equals 3.12 seconds. The time it takes to go from here to here is the time it takes to go from here to here. Quite simple. The only equation I'm ever going to use in the x direction, so I've got 9 equals delta x over 3.12. So how far does it go? You solve that and we get 28.1 meters. Okay, so that's our answer for part C. Part D, is it a field goal? Well, we're given that the goalpost is 23 meters away from the kicker. It does go 28.1 meters, so it does go far enough. We know that. But the question now is, does it go high enough to make it over the goalpost, which is 3 meters high? Now here's something, the 3 meters, we're told that's the height of the goalpost, but really we're not going to use that until the very end. Okay, so we've got goalposts here. I drew it so it looks like we do make it over, but really I don't know. Okay, so we're looking for the height right here. So really we're going to find the height of the football at that point and then compare it to 3 meters. If we're over 3 meters, we make it. If we're under 3 meters, it's going to fall short. Okay, so part D over here, we're looking in the y direction. We're looking for that height. Okay, we know our initial velocity, 15.6 meters per second. Acceleration, -10 meters per second squared. Do we know the velocity in the y direction at this point? I don't. And then the only other option is time. And time is usually the key for these projectiles because that's what's common between the x and the y directions. So let's look in the x direction. All right, we know our velocity is 9 meters per second. The goalpost is located 23 meters away, so our displacement in the x direction, 23 meters. And yeah, we can get time now. So v equals delta x over t, so 9 equals 23 over time. Time equals 2.56. So we use that over here. Okay, now it looks like we're going to use the delta x equals v naught t plus 1/2 at squared. So 15.6, and then our time 2.56. I'm going to end up going at an angle here. Plus 1/2, -10, 2.56 squared. So we solve that for our displacement in the y direction, and we get 7.2 meters. That's good news for the kicker. 7.2 meters is greater than the height of the crossbar, so the field goal is good. And there we have it.